Welcome, everyone, and thank you for being here with us this evening. This is our second online meetup with JavaBin, and this is a new series that we will do each week now, continuing for a time being. Just some quick notes before we start. If you have any questions, please use the comment field, and we will let Kevlin answer those after the talk. So please, if you have any questions, please just write it in the comment field, and we will make sure to take them in the end. So JavaBin is the Norwegian Java user group. We are a voluntary, completely non-profit driven group. We organize JavaZone conference each year, and we run meetups in 8 different regions of Norway. And today we have a very special guest with us today, Kevlin Henney. I'm very proud to be able to host this meeting, and it's sure a meetup that we have been looking forward to. So I will just hand the word to you, Kevlin, and I wish everyone a good evening, and we will talk to you in the end of this session.
Okay, cool. Right. Thank you very much, Dervish. Hope everybody's lockdown is at least interesting, if nothing else. So obviously, what we're going to talk about this evening is nothing to do with that. In fact, we're going to go about as far away from the troubles of the world as we can possibly imagine, and look into Lambdas. And I'm going to look across Lambdas from the original Lambda calculus, find out what is this stuff, because everybody's got Lambdas. So what is this stuff, and what do people mean by it, and where does this stuff actually come from? And I'll also mention a little bit about things I've discovered as I've gone through. I don't have my first degree was not in computer science, and in fact, even in my computer science qualification, I don't really think we covered Lambdas. We covered various calculi, but that was not really one of them. So a lot of this stuff came at different times in my life. So first thing we need to do is have fun with screen share. So let me just let's get that slide going. Okay. So yeah, let's talk about this. People keep talking about this, and it's a very fine letter. And honestly, if I had to pick one letter for the Greek alphabet that I have a particular fondness for, this is probably one of my top 3. And yes, you can actually have favorite letters in other alphabets, but it has a number of associations with it. So for some people, they hear the word Lambda and they think AWS, which it's an amazing piece of marketing by Amazon, has absolutely nothing to do with Lambda calculus or Lambdas in programming languages at all. It's just I think they're just vaguely trying to jump on a bandwagon, and it sounds a lot sexier than functions as a service. There's a whole generation of people who will permanently associate this symbol with the game Half-Life. This comes from the decay constant in physics, and obviously physicists are a little bit short of symbols, so it also means wavelength. And then there's calculus, which is the one that we're interested in this evening. And I will get to why is it called Lambda calculus? Why Lambda? I'll get to that one a bit later. So where does it actually come from? Well, it kind of comes from this paper. Well, strictly speaking, it comes from another paper. But Alonzo Church, American mathematician, and in 1936 wrote this paper, An Unsolvable Problem of Elementary Number Theory. And in it, he introduced Lambda calculus. And he had actually included it in a paper in 1932, but apparently there were some issues with that he fixed in this paper. And I've not been able to find the 1932 paper anywhere. So if anybody's got a link to it or can dig out a copy, that'd be much appreciated. I found the reference, but not the original paper. But that's almost all irrelevant because I can barely read this one. I'm not a mathematician by training, and after a few pages, I find myself having to really go back over this stuff. So if you have a strong maths background, this may open up even more than I found in there. I think that's kind of an interesting thing. We go back to the 1930s. The 1930s were a time of huge change. It's not much of an overstatement to say that it was a lot of issues in terms of politics and political change, but actually also in terms of science and mathematics. There's this kind of sense that at the end of the 18th century, a lot of things were considered to be almost finished. Mathematics was almost finished. Science, people felt they could see the end of where it was. It's just a few more things they needed to work out. And then this brilliant Victorian vision of a clockwork universe, everything would be known. Everything was knowable. There was this kind of belief. And kind of a crowning achievement of this was the Principia Mathematica, published by Bertrand Russell and Alfred North Whitehead in 1911. And its idea was to show that mathematics had a solid logical foundation. It was provable. Everything was provable. But come 1931, and well, things didn't look quite so good. Kurt Gödel, young Austrian mathematician, came up with two incompleteness theorems, shattered the dream, showing that for any consistent axiomatic system, there will always be theorems that cannot be proven within the system. And this kind of also comes at the end of the 1920s, where although we felt in the early 1900s, you know, oh yeah, physics, there's a bit of a refinement, there's this relativity stuff, but ultimately everything's knowable. It turns out that by the time we hit the 1920s, quantum mechanics had said, actually, you know, maybe not, hold back on that. And there were some interesting things creeping in the heart of general relativity. But there are also lessons, and I think that some of the incompleteness stuff is also very interesting from a general computer science perspective. As Adrian Collier observes, one premise of many models of fairness in machine learning is that you can measure or prove the fairness of a machine learning model from within the system. And one of the things that the Gödel's incompleteness theorems demonstrate is you cannot demonstrate the consistency of a system from within that system, from the properties of the model itself and perhaps the data is trained on. To show a machine learning model is fair, you need information from outside the system. And this is a kind of a general truth, whether we're talking about formal methods and formal approaches or these other applications. And it also turns, so we end up hitting this barrier, best summarized by Douglas Adams in The Hitchhiker's Guide to the Galaxy. We demand rigidly defined areas of doubt and uncertainty. This was what was going on in the 1930s. The Entscheidungsproblem, which is related to the halting problem, is what Alonzo Church, Alan Turing, and others were working on. It turns out there are some things we just cannot know. There are some things that are unknowable. And this was why Lambda calculus was invented. It was not invented, as it happens, for programming. And the first programming language to embody this was Lisp in 1960. The language was designed in the late 50s, but the first implementation did not exist until 1960. And this is where Lambdas kind of made their way from being a kind of mathematical curiosity to being something that could legitimately be considered part of the programmer's toolkit. Now, these days, they're all over the place. So let's dig around a little bit. So I found this introduction because I was digging around for something. And Ruby, if you've come across, if you've worked in Groovy, you may know that Groovy is based on Ruby. It's a kind of a Javaized and regularized version in many of its elements. But it does tidy up a few things. Ruby is a little bit looser. It's a little more evolved. And I always get confused. I'm not a Ruby programmer, but I always get confused. Ruby has a lot of different ideas of things that are Lambdas and Lambda-like. And I wanted to clarify things. So I Googled around and I found this tutorial. Despite the fancy name, a Lambda is just a function, peculiarly without a name. Now, this is actually quite important, but important for perhaps more than one reason. You may be familiar with this Phil Carlton quote, and you may not have attributed it to Phil Carlton, but there are only two hard things in computer science: cache invalidation and naming things. And there are variations of this, only two hard things: cache invalidation, naming things, and off by one errors. And there are lots of variants of that. But what I like here is that if naming things is one of the hard problems, then Lambdas have just addressed that. There we go. We don't have to worry about that. And if Lambdas, as many people think of Lambdas as being kind of the foundation of functional programming, and functional programming is all about not having side effects. So cache invalidation doesn't mean anything. So therefore, we're done. We've actually solved computer science. We can go home. We can have dinner and be satisfied. There are no more problems worthy of our attention. But back in the real world, let's go back to this. What did he actually say? It turns out Alonzo Church introduces Lambdas really quickly. He doesn't make a big deal of it. They're just, he kind of does this quite quickly, and you have to kind of slow down and look, wait a minute, what's he really doing here? And it turns out to be quite deep. So some of the basic stuff, symbols, every notation has a set of symbols. We select a particular list of symbols consisting of the symbols open curly, close curly. That makes us feel comfortable. Open, close parens, lambda, open, close square brackets, and an innumerably infinite set of symbols to be called variables. And we define the word formula to mean any finite sequence of symbols out of this list. Okay, so this is a slight variation because historically, the way we taught maths and the way we're introduced to it in numeric disciplines, and indeed the way that we're introduced to it in programming, a function is by definition a thing with a name. Fundamentally, it has a name, and it takes a parameter, and it is associates with a formula, but it is defined as a name. It has some important implications. Lambda calculus does things a slightly different way. F is no longer a name. It's an abbreviation. It's not a definitional name. That has some interesting consequences. Lambda is a kind of abstraction. It basically says what we're going to do is this is kind of a predicate over a formula, and we're going to associate that. But the functional stuff is on the right-hand side. That thing on the left of the arrow is just a convenience, but it means nothing more than that. But it also turns out that people love laws, and there are laws about lambdas. People sometimes refer to the laws of monads and so on, and mathematical or physical laws. It turns out there are three laws or three concepts that define what a lambda is. The first one, very simply, is a variable. You can name a thing. In pure lambda calculus, that thing is always going to be a lambda expression. There's another thing, abstraction. Now, we might be used to abstraction in a kind of general sense, but this is abstraction in a mathematical sense. And I happen to have, conveniently enough, a mathematics dictionary here, where I shall read from the mathematics dictionary. If I can only find the word abstraction. Abstraction, there we go. What do we got? Abstraction. There's a bunch of stuff here about generalized concepts, which is normally in software what you're used to. That's the definition one. Definition two, an operator that forms a class name or predicate from any given expression. See lambda calculus. Convenient. In other words, what we're doing is we're basically saying this is a functional abstraction. It is the ability to take this expression and give it some kind of association, and this variable will be bound over it. We'll come to that bit in a moment. And then rule number three, you can apply it. If everything is a lambda, so y is a lambda, you can apply the lambda to a parameter. So application. So these are the three things that make a lambda. Now, there are a couple of other things. Let's look at the notation I gave you before. F is an abbreviation. Now, why is that important? It's not a definition. It's an abbreviation. It basically is equivalent to the thing on the right-hand side. That means that F cannot appear on the right-hand side, which is kind of an interesting one because it basically means that lambda calculus has no concept of recursion, which for a lot of people is going to be, well, wait a minute, isn't this really important in functional programming? And the whole area of fixed point combinators is well outside the scope of this talk, but it's how you solve this. But it is basically the idea, if you want to be more traditional, this is more like a C-style macro. The name is just an abbreviation. It has no meaning beyond that. So if it requires infinite expansion, then this isn't going to work. So it's just a shorthand. There's nothing more. It's not a definition. And then you have two kinds of variables, bound variables, which come in as parameters, and free variables, which come in from outside. Now, what's really interesting about this is that in mathematics, you don't need to care about the fact that these come in from outside. There's no concept of scope in the same way that we care about in programming languages. This turned out to be an issue that had to be resolved, and we'll get to that in the story of lambdas. Now, let's take a really simple one. Let's just take the square of x. Square of x, let's do this old school style. Square of x is defined as x times x. That's great. Now I'm going to do this lambda style. I'm going to write this differently. I'm going to associate, I can still use the name, and I'm going to associate it, lambda x over x times x. A small liberty I've taken here is that pure lambda calculus doesn't have any operations like times or any types or anything like that. But simply typed lambda calculus is a very common extension. People aren't too freaked by it. This is great because if you remember just a few slides back, innumerably infinite, it turns out that Alonzo Church, he didn't invent the emoji, but he did allow the emoji. He basically said innumerably infinite. So we can do this, and this is a cross product. We can just simply substitute this. In fact, this is what is known as, these two are equivalent. This is that he had lots of different forms of equivalence. This is called alpha equivalent. And we can even change the symbol on the left-hand side. So it's literally a square, and I can apply it. The square of 7 is equivalent to the square of 7. And most importantly, it's equivalent to this. So these are all equivalent statements. This is really what we mean by this. The name is just a convenience. It just expands to that. Okay, now let's go back to this. There's kind of an interesting thing about the title. The most interesting thing about the title is the word number, because it turns out numbers are too complex. One of the things that Alonzo Church, he wanted to prove certain properties of formulae and numbers, boundedness and all this kind of stuff, and demonstrate that certain things were bounded, certain things were unbounded, therefore things that are provable, not provable, reachable, unreachable, all this kind of stuff. It turns out numbers, and you might think of integers as being fairly simple. Actually, they're quite complex. They're quite complex creatures. So he basically got rid of numbers. He's going to have a mathematical system that has no numbers, which means there are no numbers. You have to invent your own. You have to hand roll your own numbers. I mean, this is so close to the software craft movement. Why use commodity integers? You just create your own artisan-based numbers. And finally crafting, everything begins at 0. So let us create 0. Now, what's interesting about this is that it's not immediately obvious what's going on. So let me show you what 0 is going to be. That's not very exciting. I'll read it out. We seem to be having a lambda that takes an f that applies over a lambda that takes an x, and it just returns the x and ignores the f. It's not obvious why this is 0. 1 we're going to treat as being the same prefix part, the same abstraction, but actually the formula is different. We apply f to x. Again, it's not necessarily obvious why there is oneness about this, but now it starts becoming obvious. Even if you're not following, you can just go, wait a minute, there are 0 f's for 0, 1 f for 1, and 2 applications of f. F applies to x, and then the result of that is applied, f applies again. So in other words, you can kind of guess how this goes ad infinitum. So this is quite neat, because what he's basically doing is, instead of thinking of, normally when people are thinking about what are numbers, when they get to that point in the pub, if you remember pubs, when they get to that point in the pub where you're having a deep philosophical or numeric, mathematical conversation, you've had a little bit too much to drink, and somebody says, "What is a number?" That kind of gets interesting. But normally people always default to the idea of a number is a count of things. I have a pen here, I have 2 pens here. It is the amount of stuff. It is object related, not an object in the OO sense. What is interesting here is that he looks at, he's created numbers that are to do with application. So to-ness is an action, it's a process. It's not an object in the classic sense. To-ness is the application of something twice. 3-ness is the application of something 3 times. Now, I first came across this idea in this book, published in 1989, The Emperor's New Mind. I'd not really properly come across lambda calculus in a way that made as much sense to me, although I'd read Gerd Lescher-Bach by that point. This is by Roger Penrose. It's a fascinating book that gets a lot of things about AI and human cognition wrong, but it's really good on maths and physics. This is a really, about this part of this much of the book is really good. This bit is mostly speculation, and he kind of does quantum voodoo a bit, which is a bit of a shame. But the idea that we can do a few other things here, which I'm going to shorten down. But the idea of a number being the number of times you apply something is equivalent to 1, 0, and so on. Okay, now, one of the things you may have noticed is I applied lambda of f to lambda of x. It means that all lambda calculus by default you only take one parameter. Lambda calculus is automatically what is known as curried. Every function takes only one parameter, returns one result. But this is such a common idea that there's a shorthand. But this is a shorthand for this. In truth, there's no such thing as a lambda that takes two parameters in the original. But we'll give it a little. We'll say it's convenient, so we'll allow that. And we've got ways of shortening the way we write application, and we can write it like that. Okay, now this is kind of interesting because this does actually pop up in some of our programming languages. So here's 7, which looks fairly innocent. And normally, if you're thinking about it as an integer, you think maybe int, I've got 32-bit representation. Most of those bits are 0. The last 3 bits are 1, 1, 1. Yeah, that's it. We're done. Rather than thinking of it as an application of behavior, well, if you look at languages like Ruby and you look at languages like Smalltalk, actually they have this idea of 7ness is an application. You have to call a method for it. So what I can do is I can actually basically send a block of code. Conveniently enough, that's a lambda or equivalent to a lambda. I can send a block of code to 7, and I can say, this is the number of times I would like you to execute this, and pass in the current number there. And you actually see the same thing translated over into Groovy. So in other words, 7ness has now become this very different idea of a binary representation. Actually, 7ness is now an action, and then it prints out the numbers as we expect. Okay, so what does this got to do with everything else that everybody does? JavaScript and Java. As I said, lambdas have got everywhere. You may have heard of lambdas before, but perhaps you've used them in other languages. Yeah, and what was the language that made lambdas popular? What is the language that brought lambdas to the masses? It was JavaScript. Back in the mid-1990s, Brendan Eich wanted to create a scheme-like language. I'm going to come to scheme in a bit. He wanted to create a scheme-like language, and it included the idea of lambdas. Now, he didn't use the word lambda. The arrow notation wasn't written then, but the idea of functions as first-class citizens that you could pass around, that was fundamental to the language. So there's our friend Square. If we write it treating functions as values, that's the key idea here, anonymous functions effectively, I can bind it like that. I can use ECMAScript 6, arrow notation, which turns out to be remarkably convenient. And as for single expression things, it gets even more convenient. This is kind of nice and simple. And it has all the properties that we want of lambdas. I can take that name, I can apply it to 7, but actually I can treat that name as an abbreviation. And lo and behold, this works and gives exactly the same thing. Right, so let's go back to our tutorial. They're anonymous little functional spies sneaking into the rest of your code. Whew, yeah, I'm not entirely sure I like the sound of that, given that we now live in an age of awareness of surveillance and what people are doing with our data. I'm not entirely sure I want this in my code. But here, there's an interesting bias. And this bias runs all the way through how people think of lambdas. So I've had a lot of people since Java 8 go, oh, I'm doing functional programming. I'm working in Java. I'm using Java 8. I'm using lambdas and I'm using streams. That's great. You're not doing functional programming, but that's fantastic. We'll see why you're not doing functional programming in a bit. So the thing is, a lot of people associate lambdas with functional programming. It's almost as if functional programming has a monopoly on this stuff. But actually, functional programming, although it has very strong foundations there's a lot of concepts that are not necessarily tied up with lambdas. And in fact, that's kind of made very, very clear by Simon Peyton-Jones's observation that Excel is the world's most popular functional language. There is a system that has no lambdas, and I'm not entirely sure we need that extra complexity given what people currently get wrong with Excel. But if we look at where this stuff comes from, it's very natural to say, well, yes, I can see lambdas and functional programming intimately bound together. So let's go back to Lisp. What does it look like in Lisp? It looks like this. It uses particular notation, which actually has a name, as it was developed at MIT. It's called Cambridge Polish notation. It's kind of a reverse Polish. There's lambda. There's my parameter, and then I've got my reverse Polish style notation. Here's a multiplication operator, or rather my Polish notation, so it's forward Polish. My operator, and then x times x. So that's great. I can apply that to, and I can apply that to 7. So it has all the properties that we want. Now, at this point, you can build the whole of Lisp out of this. And so it's very, very obvious that there's something important here, and there's something profoundly elegant. So in XKCD, there is this thing. In fact, that particular book that I referred to has, by coincidence, a blue cover. But when I read this book, I was really impressed by how simply written it was, and the fact that back then there was no concept of portability, open source code, or anything like that. This early 60s book actually tells you how to implement Lisp, because that's the only way you're going to get it on your machine. You're not going to be able to borrow it on a floppy disk or even a tape from somebody else. So the easiest thing to do is give you a language definition and show you how to implement it. So you not only learn about what it is to program in Lisp, you learn what it is to build Lisp as well. This is kind of like your ultimate understand by building the thing guide. By the way, you don't have to pay. I can't remember how much I paid for this. It's $100 or something like that, $100 US. But you can find the PDF online if you are interested, and you have enough time now, perhaps. So back to XKCD. Last night I drifted off while reading a Lisp book. Suddenly I was bathed in a suffusion of blue. Once, just like they said, I felt a great enlightenment. I saw the naked structure of Lisp code unfold before me. Patterns and meta patterns danced, syntax faded, and I swam in the purity of the quantified conception of ideas manifest. Fantastic. And then there's even a reference to 2001. There's a 2001 joke embedded in there and a Lisp joke. If you don't understand that, that's fine. You have plenty of time now to stream 2001: A Space Odyssey. Still one of the greatest films ever made, actually. Truly, this was the language from which the gods wrought the universe. No, it's not. It's not. I mean, ostensibly, yes. Honestly, we hacked most of it together with Perl. And then the observation about quantum mechanics and figure out the regexes ourselves. Now, I'm not going to expose you to Perl, but I am going to go back to the 1960s and 1968, as I've made the 2001: A Space Odyssey reference. Algol 68. Now, Algol 68 is a language which is hugely influential. I say it's hugely influential because if you've ever used Bash or even classic Bourne shell, you will be familiar with if and phi as your if statement. That came from Algol 68. If you use the word int in any programming language, that came from Algol 68. And short and long and char, the whole idea of short integers and long integers, that came from Algol 68. The word void came from Algol 68. Struct, union. In fact, there's a nice shopping list of keywords and concepts that came from Algol 68. And Algol 68 was an unforgivingly procedural language. And we don't normally think of it as being functional, and we certainly don't think of it as being object-oriented. It was relentlessly procedural, and it was one of the best procedural languages ever. The problem is that a lot of people ended up not using it at the time. It was perceived as being too complex to implement, and honestly, the Algol 68 language definition is still much smaller than the current Java definition. So our idea of what is a big language has changed, and some of its ideas were speculative, but some of its stuff was ahead of the time. And as I say, it was a relentlessly procedural language. In other words, it's so procedural that procedures are first-class concepts in the language. That's what a procedural language should do. So what does that mean in practice? Well, everything has to have a signature. So what I'm going to do here is I'm going to show you what a procedure looks like. Specifically, I'm not going to give it a name. This is a procedure that is an anonymous procedure. And it takes a real, or basically a floating point number, and it returns a real, and it has an expression which is x times x. And I can take this and I can assign it to a variable called square. I can go ahead and I can declare it. It's a procedure that takes a real and returns a real. And then I can take it and I can apply it. And there we go. It's Lambdas by another name. So we can actually see that it has all of the right properties as well. I can just take that and apply it to 7. So it turns out that when we say that, Lambdas are important, they're important not just because some people think, oh, it's to do with functional programming. No, it's not. It's to do with something deeper. It's to do with programming. We actually see the Lambda concept is foundational in procedural thinking as well, although many of our procedural languages scrubbed it, and you're only in a few cases where you left with the idea of being able to pass pointers to functions or references to procedures around. But the original idea was, no, you should be able to pass a procedure around. If you're a procedural language, everything's a first-class procedure. But hey, guess what? They're objects as well. Lambdas in Ruby are also objects, just like everything else. It turns out that there is a unified idea. Now, there's this lovely little dialogue that was posted on Usenet a number of years ago that was kind of parodying some of the stuff that Guy Steele had written in association with Scheme. And this was, it was some good stuff. So the Venerable Master Kwok-Na was walking with his student Anton, hoping to prompt the master into a discussion. Anton said, "Master, I heard that objects are a very good thing. Is this true?" Kwok-Na looked pityingly at his student and replied, "Foolish pupil, objects are merely a poor man's closures." Okay, so here's another piece of terminology. Closure, it's a piece of terminology that pops up again in languages. So Groovy by default uses that rather than the term of Lambda. It's a term that's been around for a long time. It has been misinterpreted a couple of times, but mostly people have interpreted it correctly. It goes back to the 60s, like most of these ideas. The concept of closures was developed in the 1960s for the mechanical evaluation of expressions in the Lambda calculus. Now, that's kind of important because notice what it's done, the mechanical evaluation, because really until computers came along, you didn't really have to worry about how you were going to evaluate stuff, because the great thing about mathematics is it just kind of works on the page. You know, it's so pure, you don't even need any electricity to run it. All of the concerns of scope, lifetimes, how do we evaluate, simply don't apply. Put it on a computer, suddenly you have to care. Peter Landin defined the term closure in 1964 as having an environment part and a control part. So there's two parts to it. And this allows us to determine what is basically the difference between, sometimes what's the difference between a lambda and a closure. It's clarified here. Joel Moses credits Lambda with introducing the term closure to refer to a lambda expression whose open bindings, those free variables, in other words, names that come from outside and are not parameters, have been closed in or bound in by the lexical environment. So lexical scoping, basically, resulting in a closed expression or closure. So basically, a lambda that has no free variables is not a closure. So strictly speaking, one could say that all closures are lambdas, but not all lambdas are closures in that sense. And this was popularized. This usage was subsequently adopted by Sussman and Steele when they defined Scheme in 1975, a lexically scoped variant of Lisp. And that's what helped make it made it popular. So Gerard Sussman and Guy Steele did this work. I'll come to why they did this work in a moment. Chastised, Anton took his leave from his master and returned to his cell, intent on studying closures. He carefully read the entire Lambda the Ultimate series of paper and its cousins. That phrase, Lambda the Ultimate, some people have come across it. There is a website called Lambda the Ultimate. Often its focus is on programming language theory, design, and so on. Strong bias towards functional programming languages and more academic languages as well. But it was actually a series of papers that demonstrated how powerful lambdas were. In other words, lambda was the ultimate whatever it is that you want. It is the ultimate calculator. It is the ultimate object system. It is the ultimate procedural system. It is whatever it is. It turns out it's surprisingly effective. And he implemented a small scheme interpreter with a closure-based system. Okay, so a book that Gerard Sussman co-authored, the SICB book, Structure and Interpretation of Computer Programs. And you can see there's a lambda on the front. There you go. It's a real deal. There's a lambda on the front. This book also helped kind of popularize Scheme and presented it to a new audience. But in this book, what is interesting is that there is a scheme interpreter. And this scheme interpreter, the heart of the scheme interpreter is written in Scheme. This is kind of an interesting idea. This is actually based on the original Lisp book, but it's made more explicit here. The idea of defining a language in itself is kind of like one of those mind-blowing ideas of like, it's very complete. It's like, wow, the snake is eating its tail. It's like when I first discovered about cross-compilation. It's like, well, how do you write a C compiler in C? How does that even make sense? Of course, you need to have it. There needs to be a bootstrap step. And that's the important thing, is that people would do this stuff. And this is what Alan Kay, this kind of thing is what Alan Kay, the inventor of Smalltalk, kind of referred to as Maxwell's equations of programming. The idea that you could just reduce and say, here's how to interpret expressions in this language, written in this language. There's a homoiconicity representing yourself and yourself, as it were. And you can see that given an expression and an environment, here, evaluate, define eval, evaluate, here's an expression, here's the environment for evaluation, and here's a condition, and the condition and the consequence all the way through. Is the expression a lambda? Well, lexically close it and now pass it through and execute. But all these other things, is it an assignment? Is it an if statement? All this other stuff. But you can see it's very simple and very elegant. Now, they didn't, when Gerard Sussman and Guy Steele set out to implement the scheme, they weren't just implementing another scheme, another Lisp. There was a kind of a fad in the 1970s for trying to implement, particularly in the AI community, implementing programming languages to solve problems or to explore problems. And actually what they were after here was they wanted to understand actors. Carl Hewitt's work from around the early 1970s, 73, 74 onwards. Carl Hewitt came up with this kind of approach called actors, again, popularized in more recent years. You can see it in the Scala space, but as well in more in a purer sense in Erlang. But what makes an actor an actor? And they really wanted to understand it. And actually, I read some of Carl Hewitt's original stuff, and honestly, I understand why they were trying to figure it out. He was not exactly clear when he talked about something. Clearly, a lot of great ideas, but the way he expressed them was not obvious. So they thought, okay, we don't understand this, let's build a language. The language they built was going to be called Schema, which followed in the tradition of other languages called Planner and Mapper and so on. But it turns out their operating system only allowed 6 characters, not 7. Schema is 7, drop the last R, you've got scheme, that's where the name comes from. So what is it that makes actors actors? So they set out to explore this. And so this was their goal. What they discovered, when it was completed, we discovered the actors and the Lambda expressions were identical in implementation because of that form, that really simple form of eval. Is this a Lambda? Do the following binding. Is this an, they call them alpha expressions. Alpha A is for actor. They call them alpha expressions. And they realized that actually, because the code was so tidy, when they wrote it out, they suddenly realized, actually, wait a minute, the code for executing a Lambda is identical for the code for executing an actor, which if you wanted another software engineering lesson to take home from this, is really important. Had the code been like classic legacy enterprise code, they'd never have been able to see the similarity. But because it fitted on one page, you can go, wait a minute, these two are identical. You can see them almost adjacent to each other. So on his next walk with Quoknar, Anton attempted to impress his master by saying, "Master, I have diligently studied the matter and now understand that objects are truly a poor man's closure." Quoknar responded by hitting Anton with a stick. Now, obviously, this is clearly, inappropriate for a modern workspace, so we'll have to kind of forgive him for that. But when will you learn? Closures are a poor man's object. At that moment, Anton became enlightened. There's a unification here, that it is all of these things. Lambdas are owned by almost every paradigm. You can normally define a paradigm in terms of Lambdas. Whether it's practical to do so or not, it's a completely different question. And obviously they are more strongly associated with functional programming because Lambdas are, of course, functions. But all of those ideas, they lie at the heart of trying to understand any little fragments of code. And this was clarified as a 2009 paper from William Cook on understanding data abstraction revisited. And this paper is all about trying to understand objects and polymorphism. Looking back to a paper in 1984. And Will makes the observation Lambda calculus was the first object-oriented language. So that's 1936. Let's put the date on that. So let's actually explore the consequence of that. So this is the 7 mountains just outside Las Vegas. They are stacks of rocks, which, yes, gives me the perfect excuse to talk about stacks. The most overspecified data structure in the history of computer science. So I've got a stack here in JavaScript, and it's a little unconventional in terms of how I defined it, but it's the purest way we can get that's closest to Lambda calculus without breaking too much. The outer Lambda is a little bit gratuitous. I don't really need that. It's a function, new stack, or rather it's a variable which is bound to a Lambda that will then create the object of interest. I could have just defined this as an ordinary function, but hey, we're talking Lambdas here, so let's go the full distance here. Then we are going to bind a group of names together, effectively a Cartesian product. What it's going to do is it's going to return a thing that has these names. The names depth, top, push, and pop. We're going to bind something to these names. What are we binding to these names? We are binding Lambdas. each of these names is associated with a lambda, and these lambdas are closures over items, which is a local variable. Or put another way, it's truly a private variable. It's as local as it gets. From the outside, you cannot see this even by reflection. And so what we're doing is we are actually returning an object, a thing that is a set of bound lambdas, named bound lambdas. And this idea we see again popping up. This is structured programming from 1972. Ulu Handal and Esker Dijkstra and Tony Hall. And they make this observation: one of the most powerful mechanisms for programming structuring is the block and procedure concepts. We've got this idea of blocks, procedures, very intuitive to us. And we might go, yeah, that's great. That gives me my nesting. That gives me logical thinking. That's great. But it goes further than that. So if we take kind of an algol 60 variant, we have begin and end, open, close, curly. We have an array, which is one up to some capacity. It's an array of references to rocks. We have an integer count. You can see this is algol 60, not algol 68. Still back then, we still had to spell out integer, and we still had to spell out begin. But no, we shortened that. That's all good. And then we're going to set count to 0. Arrays of fixed size once within a block. But these are truly blocks. One of the things that got lost somewhere along the line, Pascal had it, Python has it, but you won't find it in Java. The idea that inside a block, you can nest other things. Certainly inside a block, I can nest a class, kind of an inner class, but I can't actually embed further methods or other functional things like that. So there's this idea that everything can be, if you can put it in a block, you can put it in a block. And that means you can have procedures within procedures within procedures. Depth, top, push, and pop. That's all cool. But instead of thinking of this in terms of conventional blocks, conventionally with a block, you think, okay, I enter at the top, begin, I execute all the way through, then I hit end. And then all of this stuff disappears. In other words, it has stack lifetime. It's all about stacks. It has a stack lifetime. It just disappears, and we lose those associations. We lose that state. That state is transient and gone. But what if it wasn't? What if all of that interesting stuff, those procedures and that state that you've got in this block lived on, and you could pass that block around? Well, that's a thing. And that was the premise of Simula 67. Developed by Christian Nygaard and Ulu Handal as the name suggests, 1967. A procedure which is capable of giving rise to block instances which survive its call will be known as a class, and instances will be known as objects of that class. This is objects, but you can see what they've done is they've done the closure thing. This is all based on the idea of closures, which we kind of seen with the lambdas, and that's the only the addition you need to the language. Now, of course, our notations are a little different, but this is important. As Richard Feynman, the Nobel physicist, observed, we could, of course, use any notation we want. Do not laugh at notations, invent them. They are powerful. In fact, mathematics is, to a large extent, invention of better notations, which brings us to the question of why Lambda? Of all the symbols he could have chosen, why did he not? I mean, he uses other symbols in his description, alpha equivalents, beta equivalents, and even eta. But what's going on here? Why Lambda? Well, it turns out there are a number of different stories. The problem is we don't know which one is the true one, because Alonzo Church was asked at different times in his career what was the true story. But the one I like the one I like the least is the one where he says, why not? That's not very helpful. The one I like the most is this one. What he actually wanted to do, if we take Lambda, it always applies to a single parameter. What he originally wanted to do was to do this, use a caret for abstraction, a simple idea of A abstracted. I'm going to abstract, give this an associated expression. It's this applies to a predicate. Now, this was when given to typesetters in the US. Now, if you gave this to a typesetter in France, they'd be absolutely fine with this. But typesetters in the US, they go, we don't really have those kind of funny squiggles above letters. How about this? They suggested. And he said, well, what about this? And there it was, Lambda. We find it spelled differently in various languages. So, in Lisp, as we've seen, it's called Lambda. In Python, it's called Lambda. In Haskell, it's a single stroke. It's so minimal. There's just nothing there. In classic JavaScript, it's called function. You go to Clojure, it's called fun. Apparently, there is a vowel shortage in the Clojure community. Or should it be Clojure? I don't know. But there's a deep irony, because in Clojure, Clojure is, technically speaking, it never calls these things lambdas. It always refers to them as anonymous functions. The word lambda does not occur in the documentation. This is ironic because the symbol for the language is based on a lambda, yet the one thing it doesn't have is lambdas, strictly speaking. I don't know if that's profoundly ironic or accidentally ironic. I'm going to guess that it's accidentally ironic, given that Clojure comes from the US. And Americans and irony, they don't really mix very well. Notations in other languages. This is how you can capture your closures explicitly in C++. This is how you do it in C++. This is how you introduce a lambda, which gives us a beautiful consequence that this is valid syntax in C++. You can put all the brackets together. And this is a function that takes nothing and does nothing and returns nothing. In fact, here it is returning nothing. Yeah, this is the application of it, and you get nothing. In JavaScript, C#, and Scala, we use the thick arrow. Java, Ruby, and Groovy decide to go for a thin arrow. So if I want to do nothing in Java, I'm going to do it like this. But that leads to a question. How do I do what I just did in C++? How do I execute that? Well, it turns out that although they are called lambdas in Java, the one thing Java doesn't have is lambdas. Although they're not called lambdas in Clojure, the one thing it does have is definitely lambdas. Yeah, so these aren't lambdas in Java. Now, why not? Well, let's go and have a look at Haskell, which is ultimate in terms of minimal notation. Lambda of x, and this is your x squared. In the Haskell interpreter, and now I'm no Haskell expert, but you know, I'm a Haskell tourist. I can go in there and I can ask for the type of this expression. I get the type of the expression, and it tells me it's to do with a class of numbers, and it shows me, yeah, it's got a type. Very simple idea. This is an expression. It has a type. And this is what we've been taught since we first learned about values and expressions in programming languages. If it's a value, you know, if it's an expression, it yields a value. Values have types. It's as simple as that. There's no ambiguity here, and this is the type of this. I can do this in Python. I can actually ask explicitly what's the type, and it'll tell me this is a class of functions because everything is an object, and including functions. So that's all good. What happens if I do this in Java? Well, I'm not allowed to ask for the type of arbitrary expressions, but I can try and deduce the type using the new var. But if I do this, I get a compilation error. Now, this is partly because these are not really expressions, and there's a little bit of a workaround in the language, a thing called a poly expression, and it exists for other reasons. But it turns out that lambdas don't really have, they're not values. They don't have a type. You can kind of find, you can try and hide behind the language of poly expressions, but lambdas do not denote a value. They do not denote objects. They do not denote something in the Java type system. They are merely a syntactic form. The objects only come into existence when you sum them out of the void. If you, but this on its own does not, but this is the curious thing. We would normally say, well, hang on, clearly in this case, I have a problem because X could be an int, it could be a short, it's not clear what set. It belongs to a set of possible types, the types that could take a multiplication operator. So perhaps that's why it's ambiguous here. Yeah, I accept that, absolutely. There is absolutely no ambiguity about this expression. The return type is void and it takes no arguments. There is no deduction to be done here. And that's because it's not really properly an object. If I want to execute it, I have to now place it in, I have to place it in a coercion context or an invocation context, or have an assignment where the type of the left-hand side is definite. And at that point, an object is created, but it is a kind of a, yeah, it's a kind of workaround. At that point, you're no longer dealing with a lambda. You created something else, which belongs to the runtime. And if I want to cast it into something, then what is the type system? Well, Haskell has a really regular type system, and Java doesn't. In fact, these are all the things that you can currently find in Java util function. In fact, I may have missed a couple because this is an old screenshot. These are all the kind of wrapper types. Yeah, not really wrapper types, but the interfaces through which are predefined you can call, but you can create your own. They don't have to be these. You can create anything that satisfies the demands of what is known as a functional interface, a single method. And is there in Java a regular way of calling it? Well, no, there isn't, because some of these use the word apply, some of them use the word test, some of them use the word accept, some of them use the word get. Actually, none of those apply in this context. The one we're actually interested in is run. We use a runnable here. So there's this curious thing that lambdas aren't lambdas. It turns out of the three laws, we can't do application. Application is done by enlisting an external mechanical piece of conversion. You have to say, I now want that. It's a bit like somebody giving you money and saying, yeah, you can go to the shop and spend it, except you can't. If you want to, this is not actually worth something. It's a promise of something. You have to go to somebody else, turn it into real money, choose your exchange, and then you can use it. But that means this is not money. It's a promise of money. It's meta money, but it's not actually money in itself. In the same way, Bitcoin is not a currency. Yeah, it's lambdas in Java are not lambdas. So let's go back to Hitchhiker's Guide to the Galaxy. Oh God, muttered Ford, slumped against a bulkhead and started counting to 10. He was desperately worried that one day sentient life forms would forget how to do this. Only by counting could humans demonstrate their independence of computers. Let's go back to this. If you remember, we created our number system. What I'm going to do here is I'm going to leave it long form, and I'm going to leave it long form for a very simple reason. It turns out the one language that you can do this very easily in is JavaScript. You can actually go and convert. Of course, we have to create our own number system. Java already has 0 and 1, so I'm going to have to use underscores here to differentiate my 0 from JavaScript 0. But you can see I've got all the other stuff going on here. I'm going to use a different color to encode. I'm going to say this is stuff I'm bringing in from JavaScript, because if 0 is zeroness, then how does this work? Well, let me show this with a regular JavaScript expression. Funny enough, it's also a lambda. You take n, you return n plus 1. Now, when I apply, so this is the zeroness of this. So when we apply it to, let's say, one of JavaScript's built-in numbers, when we apply it to 0, we get 0. Nothing exciting there. When we apply it, when we apply oneness to this, then the successor of 0 is 1. When we apply two-ness to this, then we're applying the n plus 1 transformation to the result of the n plus 1 transformation on 0. We get 2. So in other words, we actually make good our promise that numbers are their degree of application. Okay, so 6 is 6ness of this expression. And if we start at 0, we do that. But we can do it with suffixes as well. We don't have to put in numbers. I can do it like this. I can do it with string concatenation. So in other words, 6, this is unary notation. 6 gives me 6ness of 1. And that's kind of cute. So let's go and define square. Square can be defined like this. And it is the application of m to itself. It is the two-ness of that. In other words, if I take square of 7, then it is the 7ness of 7ness. Yeah, if you apply 7 to 7, then that's 7 times 7, quite literally. And let's apply that to n plus 1 against 0, and we get the answer you've been waiting for all of this talk is 49. Finally, we have a number. But it is this idea of the numbers being an action. Now, but it doesn't just stop. This is called a these are called church numerals. Church encoding doesn't just stop with the integers. Church allowed you to invent a whole system, and this has been explored in great depth. So here's this fellow, George Boole, who gave his name generously to the Boolean data type. He formalized propositional calculus in the 19th century with a gloriously Victorian book title name. You'll notice that the way it's often discussed when people quote it these days, they talk about it as George Boole's The Laws of Thought. The Victorian book title, the full title, is an investigation of the laws of thought on which are founded the mathematical theories of logic and probabilities. People don't make book titles like that anymore. So let's talk about truth for a moment. In the post-truth era, here's what true is, here is what false is, and let's do a church encoding. Now, this is kind of interesting because what we've got here is we're saying, given two parameters, truth is against two parameters is the first one and falsehood is the second one. So what you do is you apply this expression to two other parameters. And then depending on whether your expression is true or false, it will return either the first or the second. This is kind of interesting. This is almost like a polymorphic thing. And actually we see this is actually embedded as a concept in Smalltalk, the kind of like most object-oriented, original object-oriented language. So here's a little bit of Smalltalk. I thought I'd sneak that one in. 7 times 7, let's say it's, is it less than some limit that we've set? And this is what an if-else statement looks like in and some of this notation may be familiar to you if you've used Objective-C, but 7 times 7 gives you an integer object. You then send it a less than limit comparison. That gives you a Boolean object. That is a truth. Then you send a request against it. If true, here is a block of code, a lambda, as it happens. If false, here is another block of code. And so therefore you send it a message. And true is a class. And the implementation of the if true, if false method for true is we'll ignore the second one and we'll evaluate the first one to do, and we'll return that value. That's what little caret's for. False does it the other way around. It returns the other one. It evaluates the other one. So in other words, it turns out that Smalltalk doesn't just do its integers kind of with a nod towards the church idea of church numerals. It actually does have a polymorphic Boolean model, a polymorphic conditional model that is actually based on church encoding of Booleans. Now, this is an interesting thing, and this one I completely missed the first time I ever saw it. It turns out that if that's our definition of false, we can write it like this. We can also write it like this, which is our definition of 0, which for anybody who's ever wondered, is that just a C hack? It actually turns out, no, it's fundamental. It's a fundamental concept. Falsehood and 0 are kind of bound together, or rather can be bound together. It's a design choice there. But you can go further, and this is kind of where we're going to kind of sort of, I'm not going to go much beyond this except for a bit of fun at the end. I can do more church encodings. I can create pairs. I can abstract pairs of things using this kind of functional approach, functions that wrap functions. And then when you ask them what's the first value of a pair, it will be a function that returns whatever your first one was, X. What's your second? It'll return Y. Turns out we've already seen these. These forms are equivalent to true and false. So there's something fundamental about pairs in this. If we wanted, we could define nil as a kind of a special empty value, and we could change the names of these. Cons, car, coulda, nil. These are the very same names that are, in other words, you can create lists. Cons is the Lisp for construct a list. Car is please return me the head, the first element of this pair of pairs of pairs of pairs of pairs. Coulda is the tail, and nil, well, that's just the end of it. So we come back to Lisp, which is kind of cool. So let's close on an example that if your brains still have not melted through all of this, let's close with an example that will melt your brain. Fizzbuzz was invented to avoid the awkwardness of realizing that nobody in the room can binary search an array. So let us do Fizzbuzz, which is clearly the greatest computational problem faced by developers today. Okay, so we've got some Groovy. Here's a definition of Fizzbuzz. If you're not sure what Fizzbuzz is, historically it's a drinking game, but also a teaching game for arithmetic. You count 1, 2, 3, but every number divisible by 3 you replace with fizz. 4, 5, every number divisible by 5 is buzz, and every number divisible by 4, 3, and 5, 15, multiples of 15, is Fizzbuzz. And so therefore it's a drinking game, because if you get this wrong, then you have to take a drink, and it all goes downhill from there. So that's not a very exciting implementation, but it's a very common implementation. I put in a few notes of regularity. I could have written this difference. I don't need to do the plus equals there. But for regularity, we've got this idea: start with empty. If it's modulo 3, add fizz, concatenate fizz. If it's mod 5, then concatenate buzz. You get the 15 case for free, which is kind of nice. And everybody goes, well, the first time they discover this, they go, oh, this is cool. But we also need to stop and say, well, hang on, but what if it's not either of these? It's not just empty. If there is no result, if it remains empty, then we're actually just going to use the number itself. 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, and so on. Now, there's this really interesting and slightly crazy paper and talk by Maciej Pirog, which is really cool. And it takes a long way around to get to this really interesting conclusion, but it's quite educational. Fizzbuzz in Haskell by embedding a DSL. The default action is executed only if some previous actions were not executed. In other words, we only execute this if we didn't execute any of these. In other words, there is a sequential dependency here. There is a state dependency here. And we might say, well, let's get clever. You know, you're playing with Groovy. Let's get clever and see if we can get around this constraint. And so you've got this. Oh, by the way, this is definitely not safe for work. Do not do this at work. So we can kind of set up a map or associative array. Fizz will get n mod 3 and default to empty, and then we'll concatenate that and say, okay, we'll get mod n. So therefore, if it's divisible by 3, it looks up 0. We get fizz. Otherwise, there's nothing there, so we use empty. And we might say, yeah, this is really clever. Look, I've not used any if statements. Yeah, that's true, except for this if here. The Elvis operator is an if. If the left-hand side is empty, then we execute the right-hand side. Otherwise, we don't. So there's an if. We still have the sequential dependency. So Pirog asks, we ask if we can accomplish this without having to check the conditions for the previous actions twice. Because what we're doing is we're checking divisibility by 3 effectively and divisibility by 5 effectively twice, because we're saying, first of all, we mod it, and then we check, did we change anything? Now, we might intuitively say, no, I'm going to do this in a more functional way. I'm going to do, you know, a pure if and results. If n mod 15, if it's divisible by 15, Fizzbuzz. If it's divisible by 3, fizz, divisible by 5, buzz, otherwise then. And we might say we've never checked the same condition twice. We've never had to do a sequential dependency or a state dependency. We've never just checked. Did we check that already? Well, the problem is that's not true. When we decompose it into its natural parts, yeah, of course, this is equivalent to n mod 3, n mod 5. So yeah, we are actually checking this twice, and there's our else there. So can we make the control flow follow the information flow without losing modularity? And it turns out he presents a way to do this in his paper. We'll need to set up a few things. We're going to set up a simple function. So this is a Lambda, effectively. ID, you pass it an argument, it returns the argument. In fact, in Groovy, there's a shorthand. If you don't name the argument, it's it. It gets this from the Lisp world. And yeah, that's fine. It returns itself. Then we're going to take the value of something. And this is basically, we're going to create a Lambda that's bound to a value, and then whenever you apply it to anything, it'll return that original value. It'll ignore whatever's it's been applied to. It'll always return the original value. Again, we can shorthand that to this. Then we can say fizz. We decide what fizz is going to be. If the number is divisible by 3, then it's going to be identity. Otherwise, we're going to bind together fizz plus the application of whatever our argument is to empty. We're going to do the same thing for buzz. And then we're going to apply it like this. And at this point, you're going like, I did not realize that 5 lines of code could actually be that cryptic. Yes, it can. And obviously, I'm definitely saying don't do this at work. But we can go ahead and check. We can ask the range 1 to 100 to print us what is the Fizzbuzz of everything, and it works out just fine. So that it always takes me a while to reconstruct that, and I generally forget without guidance, but it is interesting. I've tried implementing that in a number of languages, and it is quite an elegant way of looking at it, and it's certainly something to go and mess about with. But of course, it is definitely, don't do this at work. Do not impress your colleagues with this. But it is the most gratuitous example of Lambdas. If your colleagues say, Lambdas always make my code clear, then show them that just to counterbalance it. And of course, it does submit to Anderson's law. I have yet to see any problem, however complicated, which when you looked at it in the right way, did not become still more complicated. But that brings us to a comfortable ending. To quote T.S. Eliot, we shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. We think we understand Lambdas. For years, I thought I understood Lambdas just based on a very simple idea of anonymous functions in various languages. And although I'd read about Lambdas before in various sources, it turns out I did not fully understand what they were capable of and why they're really cool. And of course, most of this stuff does not mean anything on a day-to-day basis, but it does show you where a lot of ideas unify and how things are bridged, and you kind of get a deeper understanding. Oh, at this point, I'm going to do a book plug, by the way, before we answer any questions. I'll do a book plug. Seeing as you're a Java-friendly audience, Trisha G and I have been editing a book, 97 Things Every Java Program Should Know. So we've finished the edits on that. It's kind of in production. We've got a few copy edits and things to deal with at the moment. But the hard copy should be available in June. The ebook will be available definitely by June, possibly the end of May, but global situation being what it is, that's difficult to guarantee in terms of production. But that may be of interest to you, and keep your eyes open on that. So, right, I think good to go back to Dervish, and I'll stop the screen share. Let's go there, stop the screen share, and maybe handle some questions.
Yes, thank you so much, Kevlin, and well done with the talk.
Thank you very much.
We got in some questions. Let me start at the top here. First one is, are the slides available?
The current answer is not yet. The eventual consistent answer is eventually. Not sure. I can put them up on my slide share. That might be the easiest thing. If you right, okay. So here's the solution. I'll make them available, either slide share or put them in the meetup group or whatever. But I'll make those available, and I will certainly announce them on my Twitter feed. And if JavaBin could also announce that one way or another. If you're watching this and you're following either me or JavaBin, then you'll find out. And if you are watching this and you're not following either me or JavaBin, then hey, guess what? Your opportunity to just follow is right there. It's one mouse click away.
The second one was, what inspired you to take this deep dive into Lambdas?
Oh, that's a really good question. I think it. Okay, so I did a talk actually at Java Zone about 4 years ago. I could be wrong. I could be off by one. 4 or 5 years ago, that was on paradigms. But I've had a long interest in how programming paradigms kind of fade into one another. There's no hard and fast boundary. You don't suddenly say, right, I'm now leaving procedural paradigm and suddenly I'm in the functional paradigm. I'm now leaving the functional paradigm. I'm in the relational paradigm. I'm leaving the relational paradigm. I'm in the object paradigm. They don't have fixed borders. They often blur into one another. And sometimes the way you value a feature depends on where you're coming from. So it turns out that many people are already familiar with ideas. Sometimes one person from one point of view is looking at it going, oh, I see that is functional, whereas somebody else is looking at that and they're going, oh, I think of that in terms of scripting. As a scripting paradigm, we can actually characterize that as a paradigm. And I'm very interested in the fact that like paradigms are a little more slippery than we sometimes think, and they seem to have a lot in common, or rather that you can take knowledge from one paradigm and discover you already knew something about the paradigms next door. But in doing this, I started looking at this, and I expanded that talk into a deeper exploration of programming languages. And I kept coming back to how lots of these things were bound through common features. And one of them was Lambdas. And actually that idea of blocks and closures is something I've had a long interest in. And I think probably the William Cook paper first made me properly aware of that. And so I did a talk many years ago at Java Zones, probably 2010, 2011, called "It is Possible to Do Object-Oriented Programming in Java," which is actually a quote taken from William Cook's paper, where I looked at this in some detail, but I don't think I'd really appreciated the whole church encoding thing. And then I was prompted by another paper a crazy piece of code a few years ago done by Tom Stewart, called Refactoring to Nothing. It's based on Ruby, where he used church encodings, and I'd completely forgotten about the existence of this. But what he did is he solved Fizzbuzz, but starting with no numbers. He basically programming with nothing. He said, right, let's just use Lambdas and create our own number system. and our own loops and everything. And so he built up from nothing a Fizzbuzz program. And I remember looking at this and thinking, wait a minute, he's using church encodings. And I completely forgotten about this stuff. And that eventually, all of this made me think, you know what, maybe one day there's a talk just on Lambdas, given that more people are familiar with them now. I've kind of got an excuse there to, why don't we go back and see what else there is here? It turns out the idea is much deeper, not necessarily more useful, but if you're somebody who likes to really understand how everything's connected, then there's an appeal here of like, oh, okay, that, and that's this idea. So ultimately, it was, for me, to take the deep dive was these own little bits of my own knowledge, these little islands coming together. And I thought, well, let's just try and put something together in a talk and see what comes out. So yeah, but thank you for that question.
Yeah. And there is a question about Lambda versus Kappa. Is that something you have insights to?
I don't, I'm afraid. So that maybe that's a future talk.
Yeah. There's another question, whether if you have a link to understanding data abstraction.
Yes. In fact, that's one of the interesting things is that what made me the data abstraction. I if you like, I left off just as we were getting to the data abstraction bit. That idea that you could use the application of a function as a way of grouping data. If I can abstract numbers like that. And we got to pairs, and it turns out you can create lists from pairs. It turns out that when you see how pairs are done, that's not in the original paper, I don't think, but it's certainly in the Lambda work that came afterwards. When you realize, wait a minute, I can describe not just simple types, I can do aggregate types like this, it's just like there's a realization, oh, you could actually theoretically describe all kinds of data like this. And then you see the data abstraction stuff done a different way. So there's two ways of doing this, kind of a bit close to the JavaScript stack example that I did, where Lambdas, we generalize the abstraction. So we're going to hide away, we're going to allow ourselves Cartesian products or records or objects or, well, associative arrays as they are. We're going to allow ourselves that, and then we're going to hide data we're going to hide the data. And that's kind of the area that I first was familiar with, but I wasn't as familiar with the other stuff. So yeah, data abstraction is totally open to this approach, but by two different roads, it turns out, which I found quite interesting. I only thought of it in terms of one. Yeah.
There's a question about one of the researchers that you referenced to. I really hope I will pronounce his last name correctly here now. Let's see, C-A-R horror. Is that horror in as the same as in
Tony Hall? Tony Hall. Sorry, my connection just went a bit. Is that the same Hall as in Hall logic?
Yes.
Is that what you asked? Yes, it is. Yeah. Tony Hall. It's the same Tony Hall. So just clarification, you're going C-A-R Hall. How's that? Charles Anthony, was it Richard? Probably Richard. That sounds like it fits. C-A-R, so Anthony, Tony. So that is the same Tony Hall who invented quicksort, the same Tony Hall who came up with the whole precondition, action, postconditional, given when then originally form, formal methods, Hoare triples, Hoare logic, CSP, which sometimes people reference when they talk about actors. They say, oh, the communicating sequential processes, that's kind of related to that. So yeah, it's the same Tony, it's the same Tony Hall. Yeah.
Next question is it oxymoronic and or blasphemic to use lambdas within object-oriented paradigm?
Not at all. Not at all. I think part of the observation that I would make is that a programming language that does not allow you to treat functions as an object-oriented programming language that does not allow you to treat functions or methods as if they were objects is not complete. Yeah. This is important because in Simula, this idea of being able, you could pass a block of code. That was fundamental. That was always in the language. In Smalltalk, the idea of lambdas, they're not called lambdas, they're just called blocks. They have almost no syntax to introduce them. They're just square brackets. Here's a piece of code. So a block of code is a thing. It's an instance of class block. So Lambdas are built into the language. Indeed, Alan Kay was deeply inspired by Lisp. And when you start looking closer, particularly the interpreted, the dynamically typed object-oriented languages, you start seeing there's an awful lot more of the Lisp kind of thinking in there. So it's not blasphemous at all. I would actually say it is blasphemous to not have. It's the very opposite. If your programming language does not support the idea, so Java, as my favorite example, I did a talk in 2003 where I made the claim Java is not object-oriented. It's not fully object-oriented because I cannot treat everything as an object. I said that's what an object-oriented language does. And maybe one day Java will have this. That one day has now come to pass, which is great. But it's fundamental. If it's an object-oriented language, then it needs to be in there. So yeah, Lambdas are fundamental in that sense, and I would say not blasphemous at all.
Let's see, next questions, and they are coming in. The next one is there any similarities between C function pointers and lambdas?
C function pointers and lambdas. Yes, there is. Let me just quickly change my work. Hang on, my connection's going a little bit funny here. Let me answer that question in a moment. I'll be back in a minute. Have we got anything running? Okay, I'm back. Right, is there any relationship? Yes, there is. So a function pointer, it takes us back to the definitional idea that we're, in this case, only pass around a thing that has already been defined and has a name. So it's not exactly where we want us to be. It means I always need to give something a name. But it gives that idea of I can pass first-class value. That is the less lambdas, that or function is a first-class value.
Okay. Let's see. I have a question here. It says, some say that lambdas in Java are really resource hungry. Do you have any insights into why that is?
Ooh, okay, there's two levels there. Some say, some also say they're not, and so therefore I think that's a matter of implementation. They're not intrinsically hungry. A lambda is a little piece of code. It's up to the JVM. The JVM has complete freedom as to how it chooses to implement it. So in this case, a little piece of code can just be, it could be implemented as simply an anonymous method. It can be JITted in. There's a lot of things there. So it would surprise me if they were resource hungry. They are things that may need to be garbage collected, but they are, I would not have said that they are intrinsically resource hungry. So I'm not sure. I think somebody would have to say they believe they're resource hungry, and here is an example, or for this reason. So I'm not really sure. Yeah, people often have a particular view on things, but I don't know where that one comes from.
Yeah. Let's see. Is it possible to get a list of the books that you referenced to in your talk?
That goes with the first question, actually. Everything in talk, all the links and the books, in fact, with the exception of two books, that one and that one, I'm not saying, honestly, reading a dictionary is not that exciting. You must be very bored under lockdown to want to do that. And I'm not necessarily, I think this is a really interesting book, but it's not, it's not something I'm necessarily going to recommend now. Yeah. But for computer science related stuff, that'll all be in the slides. So everything that I've mentioned is in the slides. So yeah, if you get the slides when that's up, so I'll do that later or tomorrow, then you can dig through that. Yeah.
So I have two more questions. Okay. The first one is, a recurring theme in your talks seemed to be that new ideas are actually invented earlier. History repeats itself?
Yes. I think it is. Yeah. So that's a good observation. And actually, going back to another question, that's one of the reasons I ended up doing this, because I have recently acknowledged that, and I guess over the last 3 or 4 years, I've noticed actually a lot of the stuff I'm referring to can be traced back, and it's partly my own interest in trying to understand what I was doing, both as home computing, but also in my early jobs, going back and understanding, but also the things that I used to read, and sort of realizing that actually even those early things were not early enough, that there's a continuous thread that goes back. And the one thing we're not very good at in software is understanding history. And if we understood history, it's not that I'm not going to say all of the good ideas were invented in the 1960s. I'm going to say that we did have a lot more understanding. A lot more understanding was available than we appreciate. If we had a better sense of history, then many of the breakthroughs or trends would probably come earlier. Many of these things have been held back for very simple reasons. For a lot of this stuff, it's hardware that's been holding back the software dream, or rather it's hardware that has enabled the software dream. In other words, we had the ideas, but simply didn't have the hardware that could make it happen. But I am seeing far too often people will come across an idea and they will champion it as this is the new thing. I would be much more interested if people sort of said, here is an idea and half of it is old, so you already know this. And there's another half here that is new or has been enabled because of changes in hardware. So for example, microservices, they only exist because of hardware. If you tried to do microservices 15 or 20 years ago, people would have laughed at you. Your performance would have been so bad. Network bandwidth was not available. Forking a process is a costly process. Why are you using all of this memory? Simply, that was not how people did things. That was just not an efficient way to run stuff. If you wanted to run things efficiently, you do threads in one process in memory. You're done. That's it. The idea of, I'm gonna launch something and I'm going to spread it across multiple processes and slow my whole application down and give myself network liabilities, that's just a stupid idea. Or rather, it was a stupid idea. We now have the hardware and the software infrastructure that enables that idea. But when we come to it, rather than saying this is a new idea, it's saying this is composed of a number of old ideas that have been put together in a particular way. And we can then say, and here is the one new idea. It allows us to get a faster start. It also allows us to use our previous knowledge. Every now and then I find people, sometimes when they move, I notice it particularly with programming languages, but sometimes also with infrastructures and ecosystems. It's like when they move to a new environment, because they feel like they have to throw all of their knowledge away. And that's a great shame, rather than building on it. Whereas if we look at all of our other disciplines, whether we're talking building architecture or physics or whatever, those are all kind of discovery. You build on the thing. We don't, much as I've talked about inventing your own numbers, we don't invent our own numbers. We reuse that. I don't have to invent multiplication every time. We build on the things that went before. We say, given this and that. So there's this idea that perhaps if we had a slightly better sense of history, then many of our new ideas would seem less surprising, but also more within our reach. And perhaps we would reach for them sooner. I think that's the exciting thing. But it would also means we would have a better palette of ideas we could draw from. And we could say, hey, wait a minute, here's an idea. I wonder if its time has come. I wonder if you put this idea together with this idea, if there's something new in this. And I think it would be a good generator, as it were. So yeah, I do think that we could be a bit better at history. I don't think all the answers can be found in history, but I do think a lot more than we appreciate can be found there.
Let's do one more question. Is purity, ref mutability of internal state, relevant for the original definitions of lambdas?
Okay, well, in one sense, Well, okay. So here's my cop-out answer: yes and no. I'm going to refer back to what I said in terms of mathematics. If we take mathematics as our basis of purity, then yes, it is, because that's intrinsic to the whole idea. But that was also the challenge. How do I make lambdas work in an environment? You know, all of our machines are imperative. You know, the execution of stuff that's happening on that Intel processor inside my laptop, it's very imperative. It's all about state change. It's all about the importance of sequence with respect to state change. And when I run something that is a functional piece of code, that functional, like any paradigm, because there's no objects down at that level, it's not even procedural down at the lowest level of the firmware. It is certainly imperative, but it's not necessarily what we call procedural, and it's not functional. It's not any of these paradigms. All paradigms are at some level a constructed illusion, and our choice is, when we use a paradigm, is what illusion would I like to construct? What makes it easiest for me to think about this world, or how do I want to build this software system? And I choose my lens, my way of looking at the world. So in that sense, lambdas are intrinsically pure because they're a mathematical idea, but to make them real requires the breaking of a lot of imperative eggs, as it were. But also what I find interesting is that the Lambda model has been used to try and understand state change. You know, so yeah, so in one sense, the pure view of lambdas, lambdas naturally give rise, if you do nothing else, you will end up with a pure functional-like system, or pure declarative system, might be a more accurate way of looking at it. Unless you introduce an environment where you say the environment is a this takes you into monad space, but the environment input into something is now transformed on the other side of a lambda. You're heading into academic space here, but by default, if you just think of lambdas as pure functions, because that's what they are, you don't introduce side effects in them, they lend a more natural style there, and you will end up with a purer thing. But even from the beginning, you know, Lisp is not a pure functional language. Its idea of lambdas was that it allowed state change. So you know, there's the compromises. So we'll put it another way, there's plenty for people to argue over this one. Yeah.
Yes. Kevlin, thank you so much for participating and contributing to our jug. It has been a great pleasure for us to host you today. And
thank you very much.
I want to also say thank you to everyone that has been watching. And I also want to just apologize for the slight technical challenges with the links in the beginning. And I hope you all enjoyed. If there's any questions about the meetup, if you have any questions to Kevlin, please give him a follow on Twitter. If you want to follow JavaBeans's upcoming events, please follow us on Twitter. We have a great lineup of speakers coming up in the coming weeks. And it has been a great honor for us in JavaBeans to host you, Kevlin. You are a person with a proven track record over the years, and internationally well known. So thank you from all of us in JavaBeans, and thank you all for watching. And with that, I will end this evening. So, and thank you very much, and goodbye.